So thank you very much. Let's hope that the presentation also works very well and you get value of it. So this talk is not only about Rapids, as what I was mentioning, is about the whole open source GPU ecosystem and how we're trying to get things together, how we're trying to all play together to make things as productive as possible and as useful as possible for the users. Rapids was introduced with a philosophy of open source and openness, not trying to replace anything of the wonderful existing PyData ecosystem, but trying to extend it. So when we started Rapids, we had a fundamental question. We're going to start a new machine learning, data analytics, data cleaning framework. So the most fundamental question we had is like, should we create a new array for the GPU? Should we create a new standard backed by NVIDIA to be the official GPU device array? So this comic immediately came to our minds. Well, we're going to introduce, and the funny part is that literally we started looking at how many device array implementations were in Python. There were 14 device array implementations already existing. So if we had introduced ours, it would have been the 15th one. So actually the number coincided with our famous XKCD comic, which I think is like 6 years old. It's pretty old, but it's very true. So this talk is actually about doing this. We don't want to introduce a new standards. We don't want to replace what is out there in the PyData ecosystem. We want to make things play nicely together. Now, to start with, we have to understand why Python, why this ecosystem, why we decided to introduce Rapids into our PyData ecosystem, why we didn't go in a different route, why didn't we just produce more C++ tools, why we didn't just go to Spark, the Spark world. So the thing about the Python data ecosystem is that it is a very wonderful ecosystem. It is nice. The Python language is easy for not only computer scientists, but people from mathematical backgrounds, from physics backgrounds, and it has a lot of support, not only from traditional computer science worlds. And many, many, many wonderful tools have come thanks to that. In particular examples, you have NumPy that has helped to make Python a great numerical computation language. You have things like pandas that have helped a lot to make Python great for data cleaning, data modeling, and just in general data manipulation. And you have one of the best libraries, in my opinion, that has ever existed for machine learning, scikit-learn. Very elegant with lots of algorithms available, with a lot of documentation, a really good API design that is really easy to use. Now, the counter example and why some people say, hey, why don't you go to Scala? Why don't you go to C itself or other languages? Is that particularly when I started playing a lot in the Python field in 2013, is that Python was not known for speed. Python was great for accessibility, but if you wanted production speed, if you wanted a lot of responsiveness when you were training new machine learning models, when doing new developments, Python was not necessarily the way to go. And a lot of people in 2013 were trying to begin tackling this problem. Python was orders of magnitude slower than code in C, and wonderful projects like Numba were introduced back then to allow users to start making Python a little bit faster. And Numba, for example, is a really good example of what can be done with significant effort and a lot of clever people, and it allows users to write custom functions that make Python almost as fast as C in some cases. Of course, that kind of removes a little bit of the wonderful simplicity of Python, and that wonderful simplicity is what we like. We like to see codes that look like this. You import your two libraries, you just import pandas, you import your scikit-learn, you have your data in a CSV, and in its most basic form, Python allows you to do this. 5 lines of code, and you already have a logistic regression based on your CSV, on your data set. That was unheard of in computer science 20 years ago. In C++, traditionally opening files is not exactly an easy task. Of course, so that's the field where Rapids came to exist, the PyData ecosystem, where things are easy to accomplish and makes data scientists and users very, very productive. So for anyone that was here for my colleague Bradley's talk, he went through a quick overview of how people have tackled going beyond what Python was originally capable. And I think I don't need to ask how many people here are familiar with Spark. It's not exactly new. It's not exactly the newest cool kid in the block. A lot of people have migrated to use Spark when they outgrow the possibilities of the traditional Python data science ecosystem. Pandas, single GPU, single CPU pandas, single CPU scikit-learn have limitations, and therefore when you wanna go to big data sets, many people went to Hadoop, Spark, and many distributed ecosystems, particularly the Apache Big Data ecosystem. The Apache Big Data ecosystem, including Hadoop, Pig, Spark, is wonderful, particularly in the sense of completeness. It has a lot of tools, and it's still, I would say, moderately productive for users. That said, it's not unheard of that the Apache Big Data ecosystem is more the realm of data engineers than data scientists. You require a lot more computer programming knowledge to be good Spark developer than to being a good Python developer. So Spark does help a lot with the speed problems of Python, with the scalability problems of Python, but it's not exactly the ideal solution for every scenario. And not only that, if you analyze the performance of Spark, it happens that Spark runs into the same limitation as the original Python data science ecosystem. It is CPU limited. Even when analyzing something as simple as a count, when you have a distributed Spark cluster, you end up being CPU limited. Usually before you end up maxing your memory, maxing your bandwidth, your CPU will be the bottleneck. So of course, that begs the question, well, then why don't we use an accelerator? And of course, the most popular accelerator around are GPUs. My first answer here is why we decide to use GPUs is because they're also very pretty. Look at that gold GPU. They're beautiful. Besides being beautiful, there's also big ecosystems that have been fostered for many years in the high-performance computing area. CUDA is something that has many years of development. So many people would raise, and years ago, I remember when I was doing a PhD, many people would start asking the question, why don't we use GPUs for traditional machine learning way more, for data processing, not only for deep learning? What is the thing stopping people from using GPUs? And well, there are lots of wonderful tools for GPUs, traditionally speaking, things like Thrust, COP, C++ itself, which has evolved beyond belief in the latest standards. You have OpenUCX that are orders of magnitude faster of what was traditionally available in Python. But let's see what happens if you want to program just a softmax function. Well, this is my kernel for programming a softmax function that is really fast and really optimized in C++ and CUDA. And that's half the function, actually. CUDA is great at speed. It's not compute limited, actually, and has a lot of potential. But for data scientists and for being productive at creating new machine learning models, it definitely had a lot of barriers, and it's not exactly easy to program for. If anyone is a computer scientist, they might like this. There's a lot of optimized code. It's doing cool things using shared memory. But if every time you had to create a linear regression, you have to program a loss model like this, well, that's the reason CUDA was not popular for classical machine learning 5 years ago. But that still doesn't negate the advantage. And the thing we have seen in the field, now that we are a year into Rapids, the thing is that GPUs don't get compute limited in the vast majority of cases. In the vast majority of cases, the limitation with GPUs is actually memory bandwidth, which means you can keep throwing, the more data you throw at the problem, the faster GPUs will keep performing. So that is an amazing advantage. And also, you can put up to 16 GPUs in a single server, and there's a lot of tools that we have inherited from the high-performance computing area. The HPC guys doing weather simulations, doing very hardcore mathematical algorithms, have implemented lots of great mathematical algorithms. CUDA has a lot of existing code that is wonderful. So this is the exact context that Rapids came into existence. Now, the thing is that there's still a lot of open questions. It's not only, hey, let's create then a Python wrapper around the existing CUDA code and just offer it as it is. It happens that during all these years in the Python data ecosystem, there have been many lessons learned. I remember exactly in 2013 in PyData New York, I remember going to a talk by Wes McKinney, the creator of Pandas. It's a talk that got very famous, and I recommend for you to look it in YouTube because it's very nice to look at. The title of the talk was 10 Things I Hate About Pandas. And it was just lessons that he learned while writing pandas and creating the basis of pandas. And among those many lessons, he ended up eventually going and creating a new project called Apache Arrow. Now, Apache Arrow many people are starting to be familiar with, but it's not a pandas-style library that you will end up using necessarily every day. It's more of a developer backend library that allows your tools to be better. Now, what are the main lessons that pandas try to address? Well, one big one is that if you want to do a workflow that is not just about tools of a single library, you have to do a lot of data conversion, a lot of manipulating data. For example, back in the day, even going from something as simple from a pandas data frame to scikit-learn, you have to go convert your pandas data frame into a matrix and then go to scikit-learn, which is an added complexity. And if you wanted to also use deep learning after that, well, things immediately got way more complex. So one of the big things that Apache Arrow is doing these days is creating a common column-based memory format. And therefore, any library that adheres to this memory format can talk with each other. And then the user doesn't need to worry if their data was originated in one library, if they want to use functions in another library, or even potentially languages. There is nothing stopping one having a hybrid language workflow in which you use, for example, R statistical functions, then you do Python, pandas, deep learning, and then you can use ggplot for visualizing things because, oh dear Lord, I wish we had ggplot too in Python, but that could be a talk for another day. So in this sense, Apache Arrow existed, and then we started developing the Rapids core, the tools available in Rapids. I won't repeat necessarily what are the core Rapids components, but if you visualize what are the core components of the Python data science ecosystem, it looks something like this. At least these are like the most known tools for every data scientist. You need to know in the Python world, you need to do pandas to clean your data, scikit-learn, network X if you're into graph analytics, then some deep learning framework, and some visualization. These are kind of the fundamentals. So we decided, let's not reinvent the tool, and that's kind of the motto of our project. Let's do pretty much the same stack, but just replacing the components with GPU components. For anyone that has gone to our booth or to Brad's presentation, you saw that cuDF is essentially pandas that uses the GPU. QML is essentially scikit-learn that uses the GPU. And cuGraph is just essentially network X that uses the GPU with the same code, the same API. But this talk is not about those, as much as it pains me because I'm very big into the machine learning one. This talk is more about these guys. This diagram begs the question, why in your Rapid stack are you including PyTorch, Chainer, MXNet, if those are not part of the Rapids ecosystem or the Rapids GitHub repository? Well, it happens that this is an ecosystem that is about interoperability between different projects from different people. We have worked a lot, for example, with the PyTorch guys, so that you could have a workflow in which you start in PyTorch, maybe have a deep learning, a neural network that has lots of weights, and maybe you went to Leland McKean's talk about UMAP or John's talk about UMAP, and you're like, hey, I know UMAP can be used to visualize weights in neural networks very, very nicely. Why don't I? And I know that QML introduced a new super fast UMAP implementation a few months ago. So we have worked a lot with PyTorch guys so that your workflow can start in PyTorch. You can send your Torch tensors from PyTorch into QML to apply UMAP, and we just give you the results, and you didn't have to do any conversions. You didn't have to worry who owns your data, what was the format of the data. We just work together. And that is not only with PyTorch, it's with many other libraries. The other component that is important and I wanted to emphasize here is Dask. Dask is not only a Rapids umbrella project, it's a distributed framework that is general for Python. You can use Dask without any Rapids component, totally with scikit-learn or Dask doing NumPy operations by itself. We have done a lot of contributions to Dask. Some of the key contributors to Dask are actually part of our team. This is all with this motto of we wanted to extend and embrace the open source community that already exists. So there are a few questions that I wanted to answer before moving on how things are operating with each other. The first one is we used a lot of Python in our code. And Brad showed you the diagrams more in depth of how each of our tools have different layers, primitives, and Python, and C++, and CUDA. But Python is one of our key components. In our Python code, the majority of it is not Python. Actually, it's Python. Well, we decided to embrace Python for 4 key reasons. One is that it allows us to have some static typing. For anyone that has worked in the past with static typed languages, there are certain things that are nice about them, in which when you can declare your variables as having a type. Particularly, you can, as a tool developer, you can check if your user is giving you something correct before processing things, before crashing your program, before doing crazy things, which is not necessarily the case with Python, although later versions have improved significantly in that. But Python was already statically typed. That also allowed us to go and expose CUDA code directly. Python has great interoperability with C++. So it's a very, very valuable tool for us. But not only that, the other key component I wanted to focus today in is that Python has a lot of use in the Python ecosystem under the hood for many, many, many projects. To the extent that, for example, NumPy offers a Python specific API if you want to, for example, access the pointers of the NumPy object. It's very, very easy in Python because it has integrated a lot of the NumPy API. So many, many other projects have Python-specific APIs that have allowed us to work together and make things nicer for the users. The other question that comes to rise, and the other component I emphasized, was why Dask? Well, among many other reasons, is that we could have gone and write a new distributed computing framework that was appropriate for the CUDA-based machine learning algorithms we do, but Dask is already very good for ETL, for data processing tasks, and also it's PyData native. It's very, very, very well integrated with the Python data science ecosystem, particularly with NumPy and Pandas. It was born from the necessity of parallelizing Pandas and trying to make things run faster, both in single node and multi-node, multi-CPU setups. So Dask already had the API and the idiosyncrasies of the Python data ecosystem. And that was, it sounds like something that we would just have as a secondary reason of choosing Dask, but it definitely was one of the main reasons. It totally adheres to our philosophy of embracing that open sourceness and that beauty of the Python data ecosystem. And also, it has very many other nice advantages, like it's very well deployable. It works with things like jar, to be deployed in the enterprise. So it's already enterprise capable. It's not an academic distributed environment by any means. And also, it's the most commonly used for pure Python libraries. It addresses quite some of the kind of disadvantages of the Spark approach, particularly not being Python native. You have to go through PySpark, and it's not exactly very Python-y. Dask is very, very, very Python-y. It totally follows, for example, the data frame API specification by Pandas as much as possible, the array specification by NumPy, and it just feels right if you're a Python developer. And finally, the other component that is under the hood, and I just wanted to mention because it's pretty cool and it's something that users won't know, but it's something that is being provided not only for GPUs by any means, is OpenUCX. OpenUCX is our communication library that is being plugged into Dask and other distributed libraries that accelerate things massively. It's somewhat topology-aware hardware communication layer. So essentially allows programs that are distributed to pass messages between them, but it knows how they are connected. So for example, if you have a network that has InfiniBand, it will use protocols that are good for being communicated through InfiniBand, and it will give you orders of magnitude faster speed than traditional message passing distribution frameworks and other distributed communication frameworks. Of course, it also is aware of GPUs. So if you have, for example, 2 GPUs and you decide to buy a really cool NVLink bridge, it will use the NVLink bridge. It won't go through host, and it will make your program run orders of magnitude faster. In the past, that was not true. Even if you had an NVLink bridge between 2 GPUs, if you didn't use something like OpenUCX, your program would go through the CPU memory and back to the other GPU memory. So that kind of defeated the purpose of NVLink. But OpenUCX would also work for CPU clusters, and it also has the optimization for CPU clusters. Now, the main optimization and the main way you can see the performance happen is not in the computation, and highlights one of the big complications of creating a data science robust framework is that this is in the communication and it's very hidden. It won't give you wrong results. It will just be slower unexpectedly. So if anyone has worked with Dask gives you this type of graphs in which when it tells you I'm doing computations or I'm doing communications. So before we optimized OpenUCX, you would see a graph, a chart like the one is in the first half of the slide, and the red squares in that is pure communication. The CPU or the processing tasks are waiting, just doing nothing, particularly towards the end of the task. So your task, your resources are doing exactly nothing because the communication layer is not aware that it had a faster path to send messages and to make things work together and get the data where it needed to be. After optimizations, you can see you all can see that there's a lot of less red code. That's kind of the most technical way. I will mention how much faster OpenUCX is getting, and that will make scaling to multi-GPUs and multi-node clusters way more efficient. As I mentioned, there's a lot of complexities in scaling to multi-node to multi-GPU. And how does this Rapids ecosystem looks like? Just for example, how do we create? Sorry, I had to turn to see that the screen was still on. I get paranoia sometimes. So how does our ecosystem look compared to the wonderful scikit-learn-based one that we saw to create a logistic regression with a CSV? Well, that was already the second slide. Just for anyone that missed it, it was 3 words of change. We have followed the APIs very closely to keep the Python data ecosystem as pretty as it is as much as possible. Of course, if you want to add distribution with Dask to this, you will have your Dask code added to it, but it's not Rapid's specific Dask code. It's the same Dask code you would write to parallelize pandas itself. That's the big philosophy. Now, this philosophy doesn't stop there, and well, that's a pretty graphic of how much speed up Rapids gets when you do those 3 words of change. So 100 CPU nodes are orders of magnitude slower than one GPU-based computer. But I won't go too much into that. You have seen talks about it. You can go to our website. That's a graphic from our website. Just Rapids is fast. That's the TLDR. But the main key here is we don't want to just stop at making Rapids be very Pythonic. Rapids being nice to use, we want to make it together with the existing ecosystem. I mentioned that we already follow the APIs. So we're going to be familiar. The user is not going to be scared necessarily about Rapids. But what happens when the user doesn't want to just use Rapids? So we have tried to interact with the ecosystem in many ways, and there are many proposals of how to make different Python libraries interoperable, how to make different libraries talk to each other, essentially. So we started facing a lot of complexities regarding that, and this part of the talk, you will see how many complexities and how much effort we're putting into making things work together. But that's the point. This talk, if we give it again next year, it would look totally different. This is very much something, the latest changes that have happened to these things probably were yesterday. So this is very much what is happening right now. But one good example is, for example, random forest. Everybody's using random forest these days in the form of XGBoost and LightGBM. So everybody loves XGBoost, for example, because it's, for lack of a better description, black magic that kind of just works more than it should. That's how I like to describe XGBoost. It's a really great library, don't get me wrong. I love XGBoost. I use XGBoost a lot. Sometimes it outperforms neural networks that are orders of magnitude more complicated, just because it has a great gradient boosting, but now I'm digressing, sorry. But XGBoost and LightGBM, for that matter, are performant for a CPU-based implementation. But once you want to go into production, it happens that XGBoost is hard to scale. It's not that easy to just make XGBoost perform really well in really big models, particularly when you want to do the inference side, when you want to predict observations after you have a trained model. So one of the components that we introduced was, hey, let's do a GPU-accelerated forest inference library, because we're very creative with naming. But it's just a library that allows you to do very fast inference for random forests that have been already trained with XGBoost and LightGBM. Now, the issue there is that XGBoost, LightGBM, scikit-learn for that matter, and QML ourselves, there's no standard of how do you encode the features of your trained random forests. How do you encode the coefficients of each decision tree, all the data that you have trained. So that has been a fun adventure in the past couple months. So right now, what we have achieved is that our forest inference layer can perform inference on models trained only on XGBoost and Light GBM, with scikit-learn coming soon, and QML itself even later after scikit-learn, which is kind of funny to think about. Our own random forest cannot be inferenced with the forest inference layer because we were focused on accelerating inference from XGBoost, which is kind of the poster child of this situation. Now, why was that? Well, we're outperforming the inference by XGBoost by 30 times, as we kind of expect from GPU-based things. But it has been a lot of work because there is no standard. So we have started to push standards for our interoperability in many, many other ways. And there have been 3 or 4 main ways, 3 or 4 main standards that we have been pushing. The first one was, as I mentioned in the beginning, there are 14 types of device arrays, or the GPU-based array libraries. Among them, some of them here are GPU, some of them here are CPU, but at their core, they're all arrays. So they're all memory that is contiguous, that is in CPU or in GPU. So the way NumPy has already seen this problem, and there have been proposals by NumPy itself to make libraries interoperate with each other. One of the main ones lately has been the proposal NEP18, which a better name for it is the array function standard, which is just a function that if your library implements, it can define how to apply the functions of NumPy to their objects. So it's this __ array function, in which if you have a new library that implements it, you just need to define this function __ array function that takes the name of the function that's going to be applied. So for example, min, and it takes the arguments that it applies to, and then it tells it how to apply the min to that type of object. So a good example of that is SciPy sparse matrices. You are not going to calculate the mean the same way in a NumPy array than in a SciPy sparse matrix, because one is at the sparse matrix that could be a COO matrix that is you have to transform to be able to calculate the mean, for example. So how does this look to the user? Well, actually, it's very nice. If your libraries both implement the array function, it happens that, for example, here, you can create a NumPy array, and then you can create a Dask array from the NumPy array, and then apply the NumPy, in this case, I'm applying the numpy.linalg svd function to the Dask array, and it just works, because Dask implements the array function, and it tells it, hey, when you see a Dask vector here, this is the way you're going to calculate a mean, or in this case, the svd function in a Dask array. So it's very, very nice for the users. It has a great result, but it has, and you can change the library, for example, to CuPy, which also applies the same function. And now I'm sending to NumPy CuPy arrays, which are totally GPU device arrays. It's not even CPU. But it has quite a few disadvantages that have made its adoption slower than what we would have hoped. Particularly, some of them is that it is a relatively big commitment. As you saw, it assumes that the functions you're going to apply follow the same conventions as NumPy. So if you had written a library where instead of calling the mean, you called it average, and then you had a different type of arguments, it's going to be a harder burden for your library to adopt this standard. And not only that, for things like SciPy and sparse matrices, they were following an older type of API for storing the data based on numpy.matrix instead of numpy.ndarray, which is like the modern NumPy arrays that everybody knows. And it has been a lot of work. There are GitHub issues that have lots of comments of how much work is needed to eventually be able to have SciPy matrices be just accepted by NumPy using this standard. And of course, there are, for libraries, for example, like PyTorch, there's worries of, hey, this could break backwards compatibility with the function we had written before. We have to rewrite a lot of code. So, and not only that, at the end of the day, it's tricky to be transparent to the users. If one of the libraries I was showing you in the code here is not array function aware, chances are that NumPy might invisibly transfer your data into a NumPy array, which if it's in GPU, it can be an expensive operation, apply the function and return your NumPy array, which was not what you sent it originally. And then the user could be confused or things could be performed really badly without the user even getting a warning. So those are significant disadvantages of this approach. They're having this approach called function dispatchers, which are just functions that define how to call functions. That was quite an interesting definition. But There have been more function dispatcher type of approaches. So, for example, the QuantSight guys have recently introduced something called the U-array, which kind of learns some of the lessons from the device function, the array function from NumPy, and create a new multiple dispatch mechanism that is agnostic of the NumPy API, for example. So you could have your own definition of API and still manage to adhere to a standard if everybody adheres to the U-array standard. Of course, that makes things a little more complicated from the tool development because it's a little more hard standard to understand and apply sometimes, but it definitely has advantages over the original NumPy device array. The other disadvantage that it has is that, or this advantage and disadvantage is that the user gets a lot of control. The user can choose which backend to use on their objects. So once two libraries implement the UArray interface, the user, for example, can call the UArray set backend function and tell it from here on now. I can tell, hey, use the CuPy backend for this, and then every time you send an object to, for example, np.min, it's not actually going to use NumPy, it's going to use CuPy. And then you could have a different library that can be used for that. Of course, that gives a lot of power to users, but adoption has been also beginning, but it still has the relative burden of implementation on the library developers. So there are quite a few work that will need to be done eventually to see it implemented in all the libraries like PyTorch, Numba, and many others. Now, if you have been seeing where I started the presentation, this begs the question, hey, didn't you say that Arrow started as a common memory interface so that everybody can talk with each other? Yes, absolutely. And there's a lot of things that are Arrow aware or are based on Arrow, like us, as a clear example. It has quite a few advantages for things like data frames since it's columnar based. So it allows you to do certain operations very fast. But for other libraries like machine learning, it doesn't have those advantages. So the adoption in machine learning and deep learning has been relatively slower. And also many libraries already have their existing memory format like PyTorch, MXNet, Numba, well, now the deprecated chainer, CuPy. So it's not as easy as saying, hey, everybody change to Arrow and start talking with each other. So in that sense, the way that at Rapid we have done interoperability, besides being based on Arrow, is with two more lightweight approaches than the NumPy device array interface. The NumPy device array function, sorry. There are DLPack and CUDA array interface, and the second one is very close to my heart, so I might talk a little bit better about the second one. But both are just essentially very simple kind of agreements or standards in which if you adhere to, you can see objects from the other standard. So the CUDA array interface has already been implemented by Numba, CuPy, PyTorch, and it's just a dictionary that if your objects implement, that happens that the other libraries can see that dictionary and read the data immediately. So I can get the memory pointers from a Numba array or a PyTorch array, and also, and that's the reason QML, for example, can accept PyTorch, Numba, CuPy, RMM, and of course, the general NumPy arrays. The first four, without custom code, is the same exact code because we all accept the CUDA array interface. And implementing it can be as simple as 10 to 20 lines of code, depending on certain details of your library, but it's way more lightweight. And here is kind of I'm almost running out of time, but here is kind of a very simple example of the type of workflows that I was describing as an objective at the beginning. It's a super simple example, but you're just creating a torch tensor in PyTorch. Then you are using CuPy to calculate the norm of the torch tensor without conversion or anything. And then you're calculating the dbScan clustering in that same, using the same data. That, if you notice, that just feels like magic because it was a PyTorch object that being processed by CuPy and then being processed by QML without the user needing anything and the original tensor still being there. So you can imagine how you could go back to PyTorch and still process things back in the original library. That this is the case already. There are, of course, many libraries that have not implemented CUDA interface for time. It requires, of course, also things, but the main advantage is that there are no conversions by the user. There's no memory copy underneath, so there's no loss of efficiency. there's a reduced user cognitive load. The user doesn't have to be thinking about converting the data all the time and keeping track of what data, what format their data is in and whether they can send it to a library or not. And the user still keeps a lot of control. They know what library, what function in what library they're going to be using. It's not necessarily chosen for them underneath because of a function dispatcher. Of course, it has disadvantages. Among them, memory ownership can be tricky. This is a disadvantage in the distributed environment a little bit, because when you want to redistribute data, it happens that we have to create a copy of the data. There's a loss of efficiency there we're trying to deal with. The CUDA array interface doesn't transfer the memory ownership to the library that is applying the function, so we cannot modify it, even if the user would like that. The version has been changing a little bit, so some libraries sometimes lag a little bit. And the user still keeps a lot of control. That I put it also as a disadvantage because that's a little more user cognitive load than might be ideal for first-time commerce. They might be, why doesn't this library provide all the functions I want? Why is it trying to tell me to use this other library instead? So it might also be seen as a weakness. And then finally, I'll mention DLPAC, which is a very similar standard, but it's for interoperability. It started as a standard for interoperability of deep learning libraries. So it's a tensor format that if you adhere to, then you can convert to DLPAC, and a lot of libraries can read DLPAC. QDF in particular in our libraries supports DLPAC, and therefore we can talk with PyTorch, MXNet, Chainer with conversions to DLPAC from a data frame, for example. And once again, the code ends up being very, very simple. So for example, from going from a CuPy array that supports DLPAC into a QDF data frame, which is the Pandas style data frame, you just need to convert the CuPy array to DLPAC, which depending on the data originally might not even require a copy, might just be manipulating pointers, and then QDF can receive the DLPAC function, even though CuPy is not an arrow-based array necessarily. Now, there are a few other interesting alternatives. There's things like CuPy getArray module that I will just mention that, in which the user calls the method from CuPy with an object, and then CuPy returns you the library that can apply functions to that. So here, for example, XP could be NumPy or could be CuPy, and the user doesn't need to know. But CuPy chose what was the better library to call things in that object. So then library developers and users can write library agnostic code. This is something that we're extending beyond what CuPy is doing for future development, because it's an option that allows a lot of freedom both from the developer perspective and the user perspective. Now, as you saw, there are many kind of competing approaches or different approaches. That is because interoperability can be pretty hard and tricky. As you saw, some people lack in applying in supporting the NumPy standard. Some people lack in supporting the CUDA array interface standard. So we're trying to do many approaches and seeing what happens, because this is definitely a very new field. The CUDA array interface was introduced not so long. It's in its version 2, which was introduced, I think, a month ago or so, which of course broke dependencies. So we had to deal with the lag of dependencies updating the version of the CUDA array interface. And all of this is happening very, very recently. A new version of CuPy was released 6 hours ago that resolves a bug with the CUDA array interface. So as you can see, a lot of things are moving, but at the end of the day, as this matures more, this will allow users a lot more freedom without losing the simplicity of Python, without becoming a C++ thing that you require a lot of conversions and gives you a lot of control, but with the trade-off of losing productivity of your users. And that's kind of the overview or the slightly deep dive into how interoperability is working in the GPU open source Python data science ecosystem. So I hope you have enjoyed the talk so far. It also has, I have a last slide, but I think I want to give a little bit of time to questions, 5 minutes. But it has also allows us to simplify our continuous integration test and unit tests significantly. But if you have any questions, feel free to ask. Of course, open source Rapids, feel free to join the movement, but thank you very much.
So there's a lot of tools under the hood here with Rapids. So I imagine the most difficult probably maintenance side is the incompatibilities that crop up whenever people make changes. How have you kind of recommended for people to kind of keep track of that or deal with upgrading their dependencies to keep both their models working and to not lag so far behind that stuff won't work in the future?
Yeah, so definitely there are the question, if someone here, is how to deal essentially with dependencies and conflicts of dependencies, which is a tricky problem overall in an ecosystem that evolves so fast. Rapids introduce a new version every 6 weeks. Tries to not break things, but it's impossible to guarantee that. There are quite a few strategies to be used. Among them, personally, I'm a big advocate of Conda to try to have version control of your environments. But besides that, trying to push libraries to support more of these interoperability standards will help significantly, because once you support the standards, you can regress. Your data is going to still be interoperable even beyond versions of that library that support the same standard. So, for example, if you see that scikit-learn 0.22 broke your code because whatever reason, but you had already processed some of your arrays in scikit-learn 0.22, and scikit-learn could support some of these standards, you could regress your library easily and then still process things with the same library, different version. So another thing that I didn't mention enough is that these standards can help that interoperability between different versions, because if the object still helps with things and you see that your library has bugs with different versions, then you can immediately start regressing things without having to retrain or rerun the workflow entirely from scratch. And of course, in the more general sense, things like Conda and Docker are definitely some of the best solutions that are out there, but it's a very active topic, not only for users and data scientists, but also for us developers. It's something that we're trying to solve. The Conda, I think one of the biggest possible solutions is Conda. They have done a great job, but it's still also young and evolving very, very fast. Conda Forge is a great movement. Everybody's trying to contribute to Conda Forge. We are trying to contribute to Conda Forge, but there's a lot of conversations happening, because not only is the dependencies for users, each library has a lot of dependencies that has to be taken care of at the operative system level, and that's a lot of decisions for the channels of distribution in Conda. So it's something that will improve, but for now, I would say that Docker, Conda, and standards like this are going to help significantly. And feel free to also drop a question in GitHub for any particular issue or a more specific question, or grab us offline for sure. It's something I respond a lot of users. I get a lot of those questions, and I help a lot of users, particularly in the QML machine learning repository, very, very often. Thank you very much, everybody.